All right, this is experiment 13, potential energy of a spring. This will serve as the introduction to uh, the experiment. Right now we're looking at the advanced study assignment. I don't know if there's a CI portion to this. If there is, you can disregard those. We're only doing the TI portion. And of course, for full credit for any experiment, you have to do the advanced study assignment, the laboratory report, including any graphs, and there is a graph on this one, and then the questions at the end of the laboratory report. Those are all required for full credit. So we've just discussed energy conservation, potential energy, kinetic energy, and we're going to see those demonstrated here in this lab. We're going to start with Hooke's law. We've discussed Hooke's law. The F equals minus K delta X. If you have a spring with a spring constant of K, if you stretch it, displacement downward, it's going to have an upward restoring force. If you were to compress it upward, it would have a restoring force in the down direction. That's why there's a minus sign in front of the K delta X, because it's opposite the displacement. You pull the spring down, the force is up. You push you compress the spring and push it up, then the force is down. It wants to expand back out. So there's Hooke's law. We're going to be working with this concept highlighted here. The work W, the work in the linear deformation of the spring, is the area under the F versus X curve. And we'll see that it's this triangle. You have the force, which is equal to Kx. The force plotted, force is a function of displacement. So the area under the curve here is 1/2 of the base times the height, 1/2 times force times X. That's the work done. And this slope is your spring constant. Okay, let's look over here. Work is equal to the 1/2 F times X, the height times 1/2 times the height times the base. That's equal to 1/2. Since force is equal to Kx, it's 1/2 Kx times X. So there's 1/2 Kx squared, which also happens to be the potential energy. You'll see the mu sub S is equal to 1/2 K delta X squared. So we know that when we have an oscillating mass on a spring, it goes from spring potential energy on the downward to kinetic energy to gravitational potential energy, back down to kinetic energy, down and back to spring potential energy. And it's just this constant exchange of energies. You should have seen that with the Walter Fenton demonstration on springs. So that's where you have the K plus U on one side equals K plus U on the other side. And we, using those concepts, we'll see that this 1/2 K delta Y squared minus 1/2 K, another delta Y squared is equal to mg delta Y, which is the potential energy. We're gonna measure that. And here's an alternate form that I give. You may want to use this. I'll have this in the Canvas notes. I just took the 1/2 K and took it out using the distributive property. So you have Y1 minus Y0 quantity squared minus Y2 minus Y0 quantity squared. And that's equal to mg times Y2 minus Y1. Okay, so here's the experimental procedure. You hang a mass, you see how far it stretches. You do that for 8 samples, and then you plot the data, and the slope of that data should be the spring constant. Then we're going to suspend it, and we're going to oscillate it. We're going to see its highest peak, and we'll get the potential energy, the gravitational potential energy, and see how it compares to the work under the curve. Okay, let's, here's the laboratory report. You only have 2 data tables, data table 1, data table 2, and we'll go through that in the next section. And of course, here's the questions. All right, that serves as the introduction, and let's go ahead and do a little demo in the next video.